A very good morning, students. In this video, we are going to learn the procedure for design of FIR filters using Windows. As we know, we have three different types of FIR filter design methods named as Fourier series method, windowing method, and the frequency sampling method. Now let's look into the procedure for design of FIR filters using this windowing method. The first step here is you have to start with the desired frequency response of the filter to be designed. It will be usually represented as HD of e power j omega, or in some book it may be represented as HD of omega also. So this is nothing but the desired frequency response. We know that based on the frequency response, the filters can be classified as low pass, high pass, band pass and band stop. Now since this is the desired response, that is the ideal response, the frequency response of these four filters will be like this. If you consider this frequency response of low pass filter, it is defined from minus pi to pi. Now since low pass filter is going to pass all the low frequencies starting from 0 to the cutoff frequency that is mentioned, we can represent the magnitude of this low pass filter as e power minus j omega alpha in the range from 0 to omega c. This is on the positive side. Likewise, on the negative side, it remains the same. From 0 to minus omega c, its magnitude is going to be e power minus j omega alpha. So, for low pass filter, the frequency response, that is the desired frequency response, will be HD of omega will be equal to e power minus j omega alpha in the range from minus omega c to omega c and 0 otherwise. Now, usually if the filter is considered to be an ideal filter, the magnitude should be taken as 1. Magnitude value should be taken as 1 in the passband. So, if it is an ideal filter, from minus omega c to omega c, you consider the magnitude as 1. For the second case of filter is linear phase FIR filter. It is called linear phase. One of the important property of FIR filter is it has linear phase response. So if the filter is to be taken as or designed as linear phase FIR filter, in such case the magnitude is e power minus j omega alpha. We are considering the design procedure for linear phase FIR filter. So in the design, that is desired response, we are taking the magnitude as e power minus j omega alpha. This is for low pass. Now coming to the high pass filter, if we consider this high pass filter, it's just the opposite of low pass filter's response. You're going to get the response of high pass filter to be just the opposite of low pass filter. So if you look into this, the same interval we have taken from minus pi to pi, and the cutoff frequency on either side is represented as minus omega c to plus omega c. Now for high pass filter, since it is going to pass only the high frequency starting from the cutoff frequency, the magnitude becomes e power minus j omega alpha only from omega c. That is, it rejects all the low frequencies till this cutoff frequency, and as soon as this cutoff frequency is reached, its magnitude becomes equal to e power minus j omega alpha in case of linear phase, and ideally we can take the magnitude as 1. So from omega c to pi, its magnitude is going to be e power minus j omega alpha. This is the same for the other side, negative side. From minus omega c to pi, its magnitude is e power minus j omega alpha. You can very simply remember these two frequency responses. That is, if you know the low pass filter's response, we are taking the same interval from minus pi, minus omega c and pi. Here again minus pi, minus omega c and pi. The same interval we are considering. So if we remember this LPF, low pass filter, from 0 to all low frequencies will be passed from 0 to omega c. So if this is known to us, we can very well draw the response for HPF, because wherever you have the magnitude here, it should be 0, and wherever the magnitude is 0 here, it should be 1 for high pass. See here, from minus pi to minus omega c, for low pass it is 0. So for high pass it should have a magnitude of e power minus j omega alpha. Likewise, from minus omega c to plus omega c, low pass is having a magnitude of e power minus j omega alpha. So it should be just the reverse of it, opposite of it. So in high pass, minus omega c to plus omega c, its magnitude is going to be 0. We don't have any value. And again, from omega c to pi, here it is 0 and here it should be e power minus j omega alpha. By this way, you can easily remember the frequency response. Okay. Likewise, if you consider this band pass filter, for band pass and band stop, we will be given two different cutoff frequencies named as lower cutoff and then upper cutoff. So band pass is going to pass a specific band of frequencies. So this side, this is the band of frequencies that it has to pass from omega c1 to omega c2. Its magnitude is e power minus j omega alpha. And the other side also, it will be from minus omega c1 to omega c2. Its magnitude is e power minus j omega alpha. Now, if we know the response of band pass, we can very well draw the response of band stop. How it is going to be? It's going to be just the reverse or opposite of this. So, here from minus pi to minus omega c2, the magnitude for band pass is 0. Whereas for band stop, it will be e power minus j omega alpha. Likewise, from minus omega c2 to minus omega c1, here the magnitude is e power minus j omega alpha, whereas for band stop it should be 0. So, just the reverse, minus omega c1 to omega c1, here it is 0, whereas for band stop it is going to have a magnitude of e power minus j omega alpha. And the other magnitude is from omega c1 to omega c2, here it is having a magnitude of e power minus j omega alpha. And in this interval, band stop is going to have 0. Here, from omega c2 to pi, its magnitude is 0. Whereas for band stop, it is going to have a magnitude of e power minus j omega alpha. So, band pass and band stop response are going to be just the opposite. Okay. So, this is the first step. You have to start with the desired response hd of omega, or you can say it as hd of e power j omega. The second step is, you have to take inverse Fourier transform of hd of omega to get hd of n. Okay. So, hd of n is given by 1 by 2 pi integral minus pi to pi hd of e power j omega, or it can be written as hd of omega e power j omega n d omega. Okay. So, after starting with this desired frequency response for the filter to be designed, you have to substitute this value of hd of omega, whatever we have chosen in the first step, here in this place, and you have to compute the inverse Fourier transform by solving this integral. And if you solve by substituting the value of hd of omega here, there will be, that is, you have to do a sequence of steps for solving this integral. Instead, you can easily remember the value of hd of n for all four types of filters. If you remember this, then no need to solve this integration. For low pass filter, hd of n is given by sin omega c n minus alpha by n minus alpha into pi. This is for linear phase FIR filter, sin omega c n minus alpha by n minus alpha into pi. If you remember this, then for high pass, the same term, in front of this term, you have to put sin n minus alpha into pi minus. So, sin n minus alpha into pi minus this low pass filters hd of n will give the high pass filters hd of n. So, sin n minus alpha into pi minus is the additional term that we have to include for high pass filter hd of n. Similarly, if you take this band pass filter, since we are going to have two different cutoff frequencies, the same format, sin omega c n minus alpha by n minus alpha into pi, denominator remains the same. But since here in band pass we are going to get two different cutoff frequencies, we are going to get two terms in the numerator, that is upper cutoff minus lower cutoff. You can remember it like this. So, sin omega c2 n minus alpha minus sine omega c1 n minus alpha by n minus alpha into pi. Then if you go for this band stop filter, as you did in high pass, the same whatever you have obtained for band pass, the same term in front of this you have to include sine n minus alpha into pi. So sine n minus alpha into pi minus of whatever we have got for band pass, the same term sine omega c2 n minus alpha minus sine omega c1 n minus alpha by n minus alpha into pi. So if we simplify this, this becomes minus sine omega c2 n minus alpha minus into minus plus sine omega c1 n minus alpha. So this is the second step. We started with the desired response hd of omega. We have determined inverse Fourier transform for it to obtain this hd of n. Now this hd of n, if you consider the length of this hd of n, it will be infinite. This is an infinite duration sequence. hd of n, since we are calculating it from minus pi to pi, this is going to be an infinite duration sequence. But we are supposed to design a finite impulse response. This hd of n is also an impulse response, but this impulse response is of infinite duration. But since we have to design a finite impulse response filter, that is, the impulse response should be finite. Okay, so for making this infinite duration sequence hd of n to a finite duration sequence, what we do in the third step is we multiply hd of n with a window function, with a function called window function w of n. Now this w of n, this is a finite duration sequence. This is a finite duration sequence. So whenever an infinite duration sequence is multiplied by a finite duration sequence, the resultant h of n, the resultant sequence, we are naming it as h of n, it is going to be a finite duration sequence. So in the third step, we have converted the infinite impulse response hd of n into a finite impulse response h of n by multiplying this with a finite window function. See, if we go out through our door and view, we are going to view many things outside. But if we look into the window, we are going to view only a finite number of things. Okay, our view is limited. Whenever we peep through a window, our view is going to be limited. The same way, if we go out of the door, we are going to view many different scenes outside. Now since this window helps us to convert the infinite duration into a finite duration, we are naming this particular sequence as window sequence, because through a window we are going to have a limited view or a finite view. That is why this method is also called as windowing method. Okay, so in the third step we have converted hd of n into h of n, and once we have obtained finite impulse response, the last step we have to find the transfer function h of z, which is the last step of the FIR filter design using windows. And for finding h of z, the formula is summation n is equal to 0 to n minus 1 h of n z power minus n. So here we are finding the transfer function, and this is going to give us the filter coefficients from h of 0 to h of n minus 1. And after obtaining this equation, the last step you can note it as, it is nothing but the fifth step is realization of if this h of z using any of the structures. We might have studied realization structures, is it not? So using any of the suitable structures like linear phase FIR filter structure, or you can use direct form structure. So we can go for realization of the h of z that we have determined in step number 4. So these are the sequence of steps that you have to go for, that you have to perform for design of FIR filters using windows. hd of omega, then find hd of n, then multiply this hd of n with the window function. Usually for solving problems, FIR design problems, 3 main windows will be asked. One is rectangular, Hamming and Hanning. The type of window will be mentioned in the problem itself. So based on the window that is mentioned, you use the appropriate window function and multiply it with hd of n, convert this into a finite duration sequence. Once this is done, then in the last step find h of z and then go for realization of h of z using any of the suitable structure. Hope you have understood this. Thank you.